Okay. I was working with the only string theorist in all of Australia, who actually moved from Adelaide to Canberra the month I moved to Canberra. Because I didn't move to Canberra to work with him, but he happened to move there, and so I was like, hey, you want a postdoc? He's like, sure. So that's pretty cool. Okay, so what we're going to do today is going to look similar to what we did last time, except of course we're going to be investigating the interior solution. To find the interior solution, we're going to have to make some assumptions, okay? Unlike the single assumption that we made last time, which was spherical symmetry, and remember we did not make the assumption of time independence, that just kind of fell out of the spherical symmetry requirement. Today we're going to be doing an interior solution, so we have to make an assumption, for example, about how the mass is distributed or so forth and so on, and we'll use the simplest assumption. But where we're really going with this is the final conclusion that if you get too much mass in a region, there's no alternative, it's going to collapse into a black hole, okay? So the point of today's analysis is just to get to the prediction of black holes, and then starting maybe at the end of this lecture if we have some time, but definitely on next Tuesday, we will start studying black holes, okay? So let me very quickly run through, once again, an electromagnetism example of an interior solution. We started out last time with the electromagnetic example of an exterior spherically symmetric solution for the electric field. Now we're going to do the interior, and this again is going to be a review for most of you. So recall, last time we solved del dot E equals 0, and we found that the exterior solution, that's the word out means you're outside of the spherically symmetric source, this was equal to Q total over 4 pi epsilon naught 1 over r squared r hat, okay? And now what we want to do is we want to do the interior solution, and for the interior solution what we're obviously going to have to solve is the solution where in the region that we're interested we actually have a source. So in this case we'll have a rho in the neighborhood, and what we would like to find is of course an expression for En. Okay? And once again, we're going to assume spherical symmetry, so we're going to assume that the source is spherically symmetric. But there's different versions of a spherically symmetric source that we could use. And we'll make use of the simplest. So if we have a circle of radius r, and then we're using the r coordinate, let's assume that the charge density, now this is an assumption, and we'll make an assumption about the configuration of stuff that's sourcing the curvature of space-time today, but for this example, we're going to assume that the charge density is a constant, which I'll just call rho star, star meaning it's a constant, star meaning it's a rock star, or a constant. It's going to be constant if the value of r is less than the radius of this circle, or this sphere actually, and it's going to be 0 if you're outside. Okay? So this is basically a constant charge density, uniform, throughout the sphere. Not on the shell, okay? Not growing linearly or decreasing, with inverse quadratic or something. It's just a constant charge density throughout the volume of this sphere. And then once you're outside, there's nothing. Okay, so it's the simplest case you can imagine. And it's also the case that we're going to assume the first time we saw the interior solution, the interior analog of Schwarzschild. Okay, so we can immediately conclude that with this 4/3 pi r cubed rho star corresponds to the total charge enclosed. All right. And then we want to solve this equation. So here we go. Let's do, once again, the integral of del dot E d3x, which is now the integral of rho star over epsilon naught d3x. And then we can transform this, as we did last time, into the integral of E dot, and this is En dot dA, which is of course 4 pi r squared times E. Okay, this is that simple integral, and we're at the radius r, which is interior to the big R, because that's why we're doing En and rho star. And then for this guy, Well, this guy's pretty simple. He's just an integral over the volume. So the volume out to our radius little r is 4/3 pi r cubed. And then we just get this constant factor, rho star epsilon naught. Okay? So we can now take this expression right here and solve it for E. And this gives us our final form of the interior solution, which is going to be Q total over 4 pi epsilon naught r over r cubed r hat. Okay? All right. I'm just substituting in this Q total here to get rid of some of these constants. Now, first and foremost, Ben, does this satisfy a boundary condition of any concern?
The electric field has to be continuous at the radius of the.
Okay, so at the radius of capital R, what does this become?
It becomes the out one.
Yeah, it becomes this expression. And then beyond capital R, it just remains the external solution. Okay, make sense? We're going to have a boundary condition today as well, because we already know the exterior solution. That's the Schwarzschild metric. So what we're trying to do is find the metric in the interior of a source, okay, which is obviously going to be more complicated. All right. And do notice that the functional dependence on R for the interior solution is different than the functional dependence on the exterior. The exterior drops off as 1 over R squared, but the interior is growing linearly with R. Okay, so back to GR. Are there any questions about this before we go? No questions? This is a reminder. All right, good. Now we're going to go back to GR. And again, you know, we solved the simplest case last time. Now you can imagine, well, the T mu is not 0, so it's going to get ugly, and you're right. Okay, so we want to consider a scenario where T mu does not equal 0. And this immediately tells us that we cannot make use of the trace reverse form of the Einstein equation like we did last time. Okay? So what we can do is we can just go back to the original form of Einstein's equations, which says the Einstein tensor, which is r mu nu, minus 1/2 the Ricci scalar times the metric, is equal to 8 pi g T mu nu. Okay? We could write this in the trace reverse form, in which case we'd have r mu nu is equal to something times T mu nu minus something times T. But if T is not 0, the right-hand side won't be 0. So it doesn't matter which form you use. So we'll just use this form. Okay? At any rate, here's the good news. Even though the differential equation we are going to try and solve is much harder than the one we solved last time, which was just that, super easy, okay? Remember, even if you can't remember the specific details, just remember last time we made a hell of a lot of progress before we even touched the differential equations. We used spherical symmetry. We used alignment of spherical surfaces, okay, to reduce the number of unknown functions, basically by coordinate choices as well. So what's good is we can take the result of all that effort as our starting point today. So in case you don't remember, that led us to ds squared is minus e to the 2 alpha rt dt squared plus e to the 2 beta rt dr squared plus r squared d omega squared. Okay? That's the basic simplified form of the metric, which originally had 10 unknown functions. Now it only has 2 unknown functions, and they are only functions of 2 variables, r and t. Okay, so a lot of progress. These are the 2 things which we're trying to solve these equations for. Okay? Now, At this point, on Tuesday, we started applying this equation, and one of the interesting things we found was that we could work in a certain set of coordinates where the time dependence of the metric could be removed. We were not making the assumption that the metric was time independent. We were just choosing a particular set of coordinates where the time dependence of the metric disappeared. Okay? You could always pick a different set of coordinates where the time dependence does happen, but the point was we could pick one set of coordinates where there was no time dependence. Okay? And that led us to the conclusion that it was stationary. Okay? We cannot do that this time because we're not going to use this equation. We're going to use this equation. Okay? But here's what we're going to do. We're going to assume no time dependence. We're going to assume no time dependence. And then we're going to solve this. The solution we get, we will then check for the consistency of the time-independent assumption. That's going to lead us to a very valuable conclusion. Okay? So, I am going to go ahead and erase t. But that is an assumption, and it is an assumption we will check at the end. Okay? So again, I'm not using the differential equations to conclude this. I'm assuming it. All right. Okay. So, first of all, I'll write down the matrix form of the metric just in case. So we have minus e to the 2 alpha, where I'm not going to put in the functional dependence on r. I just want to write things compactly. E to the 2 beta, r squared sine squared beta. And then please bear in mind that this is a curved space, okay? So the inverse metric is not the same thing as the metric. It's not like the Minkowski space case, sorry. But the inverse is easy to find. It's e to the minus 2 alpha, e to the minus 2 beta, r to the minus 2, r to the minus 2, sine to the minus 2 of theta. Okay? So the metric is diagonal, so we get that really simple. The inverse is just a 1 over all of the diagonal terms with a minus here to make sure that that term comes back as negative. Okay? Now what we can do is we can take the metric and we can feed it to Mathematica, which I will not do by hand. Okay? But we feed the metric to Mathematica, and we ask Mathematica to calculate for us. First of all, we could ask it to calculate these terms, the Ricci tensor, the Ricci scalar, and multiply by the metric. Or we can just ask it to do the Einstein tensor components. So let's do that. And if we do it, what we discover is that there are only a handful of non-zero terms. It turns out that the Einstein tensor only has non-zero terms along the diagonal. Now you might think, oh, you have a diagonal metric. That's going to make this tensor diagonal. That's not necessarily true. Okay? For this particular metric, though, it does turn out that the Einstein tensor is diagonal. But don't take this to mean that a diagonal metric means that the Einstein tensor is diagonal. Okay? All right. So, as we go, obviously I will write down what came out of Mathematica for various components of the Einstein tensor. And we'll set it equal to 8 pi g times t mu nu. Of course, this means we need a form for t mu nu. Any guesses? Thinking back on what you've learned. What form of a t mu nu might we apply?
I'm thinking maybe like just the density in top left entry.
Just the density in the top left entry, so something like this. And then zeros everywhere else. What does that correspond to?
Just the
So that's the dust. That's where I have a bunch of particles with mass. They're all at rest, and they're not moving at all. There's certainly no overall motion, because that would cause pressure and shear. But there's also no individual motion, because the individual motion would cause pressure. Okay? So this is the tensor for a dust. Dust is probably not going to be a good model for a stellar interior or a planet's interior. Okay? Anybody have another guess?
Well, if we have diagonal matrix and diagonal T-tensor, then or Einstein tensor, then we can say that the T mu should be diagonal, right?
Yes, we can assume that the diagonal, that the T mu should be diagonal. I agree with you on that. But what other diagonal form of a T mu did we study? If you were to review your notes, you'd find it. We looked at the energy momentum tensor for a perfect fluid source. Okay? Basically, this is taking a bunch of particles and saying they do not interact with each other, but they each have individualized velocities. So what this does, it does not encode any interaction between the particles, but since they're moving, they can exert pressure. So when we studied this, which was in the context of special relativity, we found that if we're in the frame where the overall motion of this is 0, that is, we're in the overall net rest frame, then the energy momentum tensor takes this form. Does everybody kind of remember that? Now, I want to ask you something, because we're not in special relativity anymore, folks. We're in curved space. So maybe this is not the way that it looks. Turns out it's not the way it looks. Okay? But you can ask yourself, what equation could I use to figure out what the energy momentum tensor looks like? Well, remember, we wrote down a tensor equation that you can use to find the energy momentum tensor of any perfect fluid. It takes the following form. Everybody remember that equation? You worked with it in your homework. It's the energy density plus the pressure times the byproduct of two 4 vectors, which are describing the net motion. Okay? So these are the 4 velocities describing the overall motion. Of course, if we're in the rest frame of the energy momentum tensor, the rest frame of this fluid, then these vectors take a very simple form. And then it's plus the pressure times the metric. Now we're in curved space, so part of the story obviously changes, and that is just the metric. Through minimal coupling, we just change the Minkowski metric to the metric of the space. We don't know it yet, but that's fine. Okay? So now we can ask, what does the energy momentum tensor now look like? Well, here we go. First of all, recall what the square of a 4 velocity must be. Jared, what must the square of a 4 velocity be?
Scalar.
It's a scalar. Is it the speed squared? Is it any helpers?
It's not like it's 1.
Yeah, it's -1. So remember, we parameterize the path through space-time by the length of the path through space-time. And that kind of trivialized the overall magnitude squared of this to -1. That's different than when we parameterize where you are by time, which is what we do in non-relativistic physics. And that makes the inner product of a velocity with itself the speed squared. We're parameterizing it not by time, but by the length of the path. So there's a trivialization argument I presented in that class. You can go back and look at it. Okay. So why am I writing this up here? Well, recall that this is just G mu nu times U mu U nu, okay? Oh, wait a minute. I know these fiducial components of G mu nu. Okay? Now, if we work in the set of coordinates for which this gas is overall at rest, then the four velocity has one non-zero component and the spatial components are zero. Okay. These spatial components are just encoding whether you have any motion with respect to this gas. And we're going to assume we're in its rest frame. Okay? But what this means is that the only non-zero terms here are going to be mu equals 0 and nu equals 0. That is this term. So we can immediately write the G00 term times U0, U0. Well, let's do that. Minus e to the minus 2 alpha times U0 squared. Okay? Well, this immediately tells me what U0 is. It's e to the alpha. Okay? Now, why am I trying to figure out what use? Oh, wait a minute. I'm going to use the sequential. Okay? So, now if we plug this into the equation, what we find is the following. T mu nu in this case is going to become e to the 2 alpha times the energy density times e to the 2 beta times the pressure times, or r squared times the pressure, and r squared sine squared theta times the pressure. Okay? So this is the form of the energy momentum tensor which we're going to work with. It obviously encodes some of the unknowns in the geometry because it depends on alpha and beta, but there's no getting around that. I mean, the metric is part of its definition. Okay? So now, once again, I'm going to take this metric and I'm going to plug it into Mathematica and tell Mathematica to give me the components of the Einstein tensor. That's the left-hand side. And now I know what to set it equal to on the right-hand side. Depends on which component I'm looking at, obviously. TT or R, theta, theta, phi. Okay? All right. Now, notice that there are 4 unknown functions. We have the function alpha of r, we have the function beta of r, but we also have the energy density and the pressure. And those are considered to be functions of r. They're not considered to be functions of theta and phi. This is spherically symmetric. But we don't yet know them, so we can list them as part of our unknowns. Okay? Now, normally, there is an equation which relates the energy density to the pressure. That's called the equation of state. We are going to find the equation of state as part of our solving process. Okay? For now, we're going to keep these as independent functions, and then we'll eventually find an expression that if we solve it, we'll find the equation of state. Now what we're going to do is we're going to make a rewrite which is inspired by the exterior solution, to which we know this solution has to match once you go to R equals big R. Okay, that's the same matching we did in the electromagnetic example. This is an interior solution. We already know the exterior solution. They should match. So what we can say is the following. We can take e to the 2 beta of r, and we can write it as 1 minus 2 g m r over little if you look back at the Schwarzschild solution, okay? If you look back at the Schwarzschild solution, which we talked about last time, you'll notice that the RR term in the solution was 1 minus 2gm over R, where m was just a constant. It was the total mass of the system. Well, obviously, this is going to nicely match that when little r goes to big R. Okay? Now, you might say, why don't we do the same thing with alpha? Why don't we take this term, because we know what it looks like in the, this term, we know what it looks like in the exterior, match it up. Turns out you can only do that with one of these, and then you have to follow the consequences of it. So we're going to do it with the RR term. Okay? And one of the reasons we do it with the RR term is because this guy actually can be rewritten in a very simple form. Okay, that's just solving for the mass as a function of R. But now, and this is where it gets really nice, if we take, hold on. Oh, yeah. I know, it's going to be a little bit weird that I'm using the GTT, but that's what I'm using. If we go ahead and take the TT component to Einstein's equation, okay, then the Einstein tensor has the following component, r to the minus 2, e to the 2 alpha minus 2 beta, times minus 1 plus e to the 2 beta plus 2 r beta prime, where prime, anywhere I write it, just means derivative with respect to r. Because r is the only thing anything depends on, and that's equal to 8 pi g e to the 2 alpha rho. Okay? The TTT component. So this is my first use of Einstein's equation. This came from Mathematica. This came from taking 8 pi g and multiplying it by the TT component of the energy momentum tensor. However, what we can do is we can replace b with m. Notice this has two unknown functions. It has beta and it has m. We can swap out beta as an unknown function for m as an unknown function. Okay, so let's do that here. This is just written in terms of the alphas and betas, but now I want to switch this from beta to m, and this takes a really sweet form. Holy shit, that's almost intuitive. Okay? All right. In this form, it is now rather easy to find an expression for m of r. M depends on r and rho depends on r. Rho is an unknown function. But we can solve this differential equation for m rather easily. Okay? And when we do so, we're going to write down the first step in a process, which I will come back to. So step number 1, we remember that m of r is simply 4 pi times the integral from 0 to r of the energy density times r squared dr prime times r prime squared dr prime. Okay? So if we know how our energy density varies with radius, then we can use this to calculate m. But m is exchangeable for beta, so we've figured out one of these unknown functions. Okay? Now, clearly, m of big R equals total mass of the object. All right? Now what I want you to consider is the RR component of Einstein's equation. Okay, once again, we feed in the metric into Mathematica and let it give us GRR. And this is going to give us R to the minus 2 times quantity 1 minus e to the 2 beta plus 2r alpha prime. And this is 8 pi g e to the 2 beta times pressure. Okay? Now once again, we can do the beta goes to m transformation. And this is going to give us the following, which I'm actually going to write up here. So this is going to give us that alpha prime is g m r plus 4 pi g r cubed p over r times r minus 2g m of r. Okay? So now we have a differential equation, which is in terms of the pressure, the mass function, which we can get from here, and then of course alpha. So we have two unknown functions in here. All right? Now you might guess that the next step would be to look at the theta theta and the phi phi components of Einstein's equations, but it turns out there's a more efficient manner. What we can do is we can make use of the energy momentum conservation, which says that del mu T mu nu equals 0. Okay? I did a brief rundown of these conservation equations when we introduced the energy momentum tensor, and we also talked about it for angular momentum and linear momentum. But this is just a statement that the energy momentum tensor is conserved, and then we can actually write this down for nu equals r. Notice the energy momentum tensor is diagonal, so if nu is equal to r, what must mu be? It must be r, that means this mu must be r. So this is really just going to be del r TRR. And if I write it down, it's going to give me rho plus p d alpha dr equals minus dp dr. Okay? Now we can take this and we can combine it with this equation and we get the following result. Okay? We can find that dp dr is equal to minus rho plus p g mr plus 4 pi g r cubed times pressure p all over r times r minus 2g mr. Okay? And this one is famously called the Tolman, Oppenheimer, Volkov equation. This is what basically supplies us with the equation of state. This is an intrinsic relationship between P and R, okay, with the mass function known. Okay? Obviously, solving that one can get a little bit ugly, but we'll do it. Now, here's what we can use this system for. Are you ready? In step A, we can use 1 to find, given one of these. Okay, so given the energy density as it transforms with R. Then we can do step A, which is to use 1 to get m of R, and hence beta of R, should we want to work in terms of beta. Okay? And then we use 3, because we're starting out being given rho. We found m, so we know everything in here except for p, so we can use this equation to find p. And then in step C, we use 2 to get alpha. Okay? Because by the time we get here, we know m, we know p, we can use this to find alpha. All right? Okay? Now you might say, well, why don't you treat this as an unknown? Why don't you have 4 unknown functions? Solve all these equations for 4 unknown functions. Well, you tell me. Why don't we treat rho as an unknown? Is there a unique solution for the energy densities distribution throughout R? No. It depends on what it is. It could be a planet, or it could be a star. Or it could be a neutron star. Those are going to have very different profiles. Okay? We have to start somewhere. We have to start with a model of the stellar interior. We can specify any one of these as the starting point, but this is the simplest one to start with. In fact, this plays a very similar role to what we did in the electromagnetism example. Okay? So we're going to start by assuming this, and then solving these equations to find the other 3 unknown functions. Okay? Are you ready? We're going to go through an example. We're going to do it all. Let's get going. All right. So we'll eliminate all of this. All right. For rho of R, let us assume that it's constant if R is less than the exterior radius, and it's 0 if R is bigger than. It's basically the same assumption we used in electromagnetism. We're just going to assume that the energy density is the same throughout. Okay? Now, I will talk about, towards the end, the flexibility of this, okay? But for now, this is our assumption. And now let's go through the steps. First of all, m of R is, this is pretty easy, 4/3 pi r cubed rho star for r less than or equal to r. And of course, 4/3 pi r cubed rho star for r greater than r. Okay? And this, of course, will give us e to the 2 beta. And that's just going to be 1 minus 8 pi g rho star r squared over 3 to the minus 1. Okay, so there's step A. So I'm taking this to be a constant. So this integral is pretty straightforward. Okay, I'm not doing anything fancy. All right? Now for B, let's go ahead and write down the Tolman Oppenheimer Volkov equation. We're going to have minus rho star plus the unknown pressure function P, G 4/3 pi r cubed rho star, plus 4 pi g r cubed times the pressure function, all over r times r minus 2g 4/3 pi r cubed times rho star. Okay? we can massage this. I will not do it for you on the board. We can massage this and solve it for P of R. And it turns out that this is rho star times the quantity R square root R minus 2gm minus the square root of R cubed minus 2gm R squared over the square root of R cubed minus 2gm R squared minus 3R times R minus 2gm. Okay? Now step C. For step C, what we get is e to the alpha of r is equal to 3/2 1 minus 2gm over r to the 1/2 minus 1/2 1 minus 2gm r squared over r cubed to the 1/2. And this is of course also valid when r is less than big R. Okay? Oh my God, it's ugly. It's so ugly. Oh, wait a minute. Can anybody tell me what e to the 2 alpha r at r equals big R is equal to? Does anybody know what the importance of this is? What role does this play?
That's in the time TT part of it.
It's the TT component of the metric. What does it become if little r is equal to big R?
The outside one that we solved for.
Exactly. I hope you're not trying to plug in little r equals big R. It should be the exterior solution, and it is. Okay? So this becomes 1 minus 2gm over big R. Okay? Which is exactly the exterior solution. Okay? Now, and of course we already know that this matches with the RR component. So basically we've just verified that our interior solution matches with the exterior solution at little r equals big R, which is what we expect. Okay? Now, I want you to consider this expression because this is where the interesting things happen. First of all, it might not be obvious, but the pressure increases as R decreases. Okay? So you could just pick values for the various constants in there and then plot this as a function of little r, and you'll discover that this quantity increases as the little r goes smaller. Does that make sense?
Does that just mean you're trying to fit more something into a smaller radius?
No, actually we're fitting, the mass density is constant. There's not more closer to the center. It's uniform.
But I mean, like, if we're, okay.
Okay? The mass density is constant, but the pressure is increasing. Okay? So let me go ahead and point out another important observation. The pressure at the center, R equals 0, blows up if the mass reaches the value 4/9 R over G from below. Okay? Well, just think about it. If I take this to be R equals 0, then for the denominator to vanish, all I need is R to the 3/2 minus 3R root R minus 2GM to go to 0. That'll make the pressure blow up. But in order for this to happen, I just need the mass to obtain that value, 4/9 R over G. Okay? Now, is an infinite pressure acceptable? The answer is no. This is a uniform density stellar object. The pressure at the center can't be infinity. Okay? So if we have a system whose mass is this value or larger, that's why I'm saying I approach it from below. As long as the mass is less than this, then we don't have to worry about the pressure going to infinity. But if the mass achieves this value or is larger, then at the center at least, the pressure is going to infinity. If the mass is larger, it might be bigger than the center. Okay? So we're finding an infinity for a particular set of values of the mass and the radius of the system. If it is inconsistent, if the mass is too big, what of our assumptions fails? We only made one assumption. Oh, we made two assumptions. What were our two assumptions? Spherical symmetry and time independence. If the mass is larger than this, you cannot have this thing sitting there static. It is going to evolve with time. Okay? What will happen? It's going to collapse. This is gravity. This is the only force involved in this model. Remember, we have a bunch of particles and they're not interacting with each other. The only force we're dealing with is gravity. Gravity is pulling things together. It's not repelling anything. So if this system is going to evolve with time, it must get smaller. Okay? Well, which of these numbers gets smaller as the system gets smaller? The radius. If this is already satisfying this and then it starts getting smaller, is it going to continue satisfying? Yes, it is. Is it going to escape? No. Okay? So basically, the way that you can think about it is that the energy density rho is responsible for the gravitational attraction that's pulling you inwards. The pressure P is the only form of an outgoing force that's balancing the gravitational attraction. So if we just think of this as a really simple system, we've got a system which has got an attractive interaction, that's gravity, but there's a repulsion which is balancing that through pressure. However, if the pressure required to do that went to infinity, it can't. And so the gravitational attraction is going to win. But once the gravitational attraction starts and it starts collapsing, the situation's only going to get worse. Okay? Now, there's a couple of issues to be addressed before we continue, we assumed that the energy density was constant. And that led us to this prediction that if something is too big compared to its radius, if the mass is too large compared to the radius, and this is a mass-radius relationship, obviously. If you have too much mass with a given radius, it's going to collapse into a black hole. That is also based on this assumption. This is actually a reasonable model for many stellar interiors. Okay? However, if you were super picky and you wanted to model your star with some, radial dependence of the energy density, there you will eventually run into Buchdahl. Who has a theorem that says, nope, it doesn't matter. It actually doesn't matter what energy density profile you give it. You'll find the same expression, that if m is bigger than 4/9 r over g, it will collapse. We obviously are not going to prove that. Okay? Here's a more pressing concern. Consider our sun. It's a nice, pretty star out there. It's still shining right now. For our sun, c squared 4/9 r of the sun over g, that's this value, okay, is 1.38 times 10 to the 27th kilograms. Okay? Well, does anybody know the mass of our sun?
It's about 10 to the 30th kilograms.
You Googled that, didn't you? I'm kidding.
No, I just had it memorized.
It's bigger than that. What did we just predict our sun will do? Turn into a black hole. Is our sun a black hole? No. Well, no, it should be happening now. Okay? So this leads us to an interesting question. Why isn't our sun collapsing?
Because the particles in the sun are definitely interacting with each other.
Exactly. What other approximation did we make in this analysis?
The particles just kind of ignore each other.
Which is called the perfect fluid. Remember, our model is that there are particles which are moving. We're obviously including their gravitational interaction. That's an integral part of the story, but we're ignoring all other interactions, including nuclear, which is a huge interaction between particles and the sun. Okay? So, taking this into account, if we took into account the nuclear interactions as part of our story, so we got away from the perfect fluid simple scenario and we included an interaction, then we would get a different answer. Okay, and our sun would be safe. All right? Now, well, hold on. So we say the nuclear interactions, they're heating things up, so increasing pressure, but which is balancing the gravitational attraction. But there's only a finite amount of fuel. Eventually, if the fuel runs out, the nuclear interactions disappear. Now you can start collapsing. Okay? Now you might think, oh, what about electromagnetism? Well, everything's neutral for the most part, so electromagnetism is not going to give us appreciable pressure. Okay? The nuclear interactions, though, can give us an appreciable pressure. So if the star runs out of fuel, it can start to collapse, which it will do. However, you can now have yet another force emerge, which will cause a pressure stopping the collapse, and that is the electron degeneracy pressure. It's a quantum mechanical effect. Okay? You can't have those electrons sitting on top of each other. Okay? If the electron degeneracy pressure is high enough to stop the collapse, then you're left with what's called a white dwarf. Okay? Chandrasekhar, one of the more famous users of general relativity, found that if the mass is larger than 1.4 times the solar mass, that's the mass of our sun, then electron degeneracy pressure won't stop it either. Okay? Now eventually, electrons and protons will fuse to create neutrons. And then you are afforded the opportunity for neutron degeneracy pressure. And if neutron degeneracy pressure is sufficient to stop the collapse, then you'll be left with a neutron star with a radius of about 10 kilometers. Okay? But if the mass is too big, even the neutron degeneracy pressure can't stop it. So we're left with the Oppenheimer-Volkov limit of 3 to 4 solar masses. If you have a spherically symmetric energy density with any kind of profile, it doesn't matter. If the mass of it is 3 to 4 times the mass of the sun, then you can't stop its collapse. Once its nuclear fuels are burnt, it will collapse into a black hole. Okay? So there was our prediction. Now, let me say a few words about black holes, and the next time we'll really dive into them. Ha, it's funny diving into black holes. Great. Anyway, okay. You guys laugh so loud. Insane. All right. So I'm going to say a few cursory words about black holes, and then next time we'll really get our feet wet and how to think about them. So first of all, what is the metric of a black hole? Well, let me ask you a question. Where is all the mass of a black hole? It's at r equals 0. So if I want the geometry of a black hole, I want the geometry everywhere, or sorry, if I want the exterior solution, I want the geometry everywhere except r equals 0. What's the geometry? It's the Schwarzschild metric. A black hole is spherically symmetric. We found the exterior solution. It's the Schwarzschild metric. Okay? So the Schwarzschild metric is the metric of a Schwarzschild black hole. And there are other black holes which we'll study, so that's why I'm calling it that. So just a reminder of what the metric looks like. Okay? Once again, this is a spherically symmetric solution to r mu nu equals 0. Now, there are two interesting points, obviously. R equals 0 is interesting. R equals 0 makes various terms go to infinity. But also, r equals 2gm is interesting. If r is 2gm, then this term is going to infinity. Now, r equals 0, it's amazing, but it's not really something we can do very much with. It's a singularity. It's big. It's big and it's big and small. It's bigness crammed into smallness. This is going to require quantum effects because it's at the smallest length scale you can imagine. Okay? over this radius can be quite large. But this radius has really interesting effects. Obviously, it's making this term go to infinity. This is where we put a lot of our focus. Does anybody know what this radius corresponds to?
The event horizon.
This is the event horizon of the black hole. And we're going to mess around a lot with the event horizon. Okay? Now, for normal astrophysical objects, both r equals 0 and r equals 2gm are internal. Okay? I went through that list last time. Okay, where I said, you know, if it's the planet Earth, if it's the sun, if it's a white dwarf, if it's a neutron star, I went through it. All of these are both internal. Okay? But remember, if these are internal to where the radius r is, then the fact that this metric is going crazy at these values is unimportant, because this is not the metric of the interior. This is only the metric of the exterior. However, for a black hole, all of this is exterior. So for a black hole, this metric applies, and the problem at 2gm is a problem. Okay? Now, some interesting observations. Black holes get a bad rap. People think black holes are sitting out there, they're sucking everything in. Let me ask you a question. If I saw a black hole, would my experience be any different than seeing a star with the same mass as the black hole? No. If I am the same distance from a black hole that I am from a star, I'm happy. Because the black hole is not pulling me any stronger than the star is. They have the same exterior geometry. Okay? Now you might say, oh, if you dive into a black hole and you pass the event horizon, things really suck. Well, go dive into a star. I mean, what the hell? Yeah, it'll burn up. Okay? But nonetheless, this is interesting. I mean, it's interesting because you won't get burnt to a crisp. Okay? So we're going to study a lot of interesting phenomena that arises as a result of that. But I'm going to end this lecture with kind of a reminder of your very first experience with a black hole and how it absolutely was not a black hole. Okay? So this is going to be kind of the comedic roundup for today. And when we come back next time, after your homework quiz, we will get into the guts and glory of the Schwarzschild black hole. So I just want to remind you of a calculation which some of you did in Physics 1 using Newtonian gravity. It is interesting, though. In Newtonian gravity, we often consider the escape velocity. Okay? So does everybody remember how to calculate the escape velocity? You want to know, if you put something on, say, the surface of a spherical object, how fast must you launch it so that it can reach infinity? It can get out of the gravitational attraction of that object. Obviously, this is a hypothetical situation because it'll hit another planet eventually, or hit another star. But we're talking about if there's only one thing in the universe, and we've got one thing on the surface, how fast do we have to launch it? And it's just the initial speed. It's not anything else. It's just the initial speed. How fast do I have to kick it in order to get it to escape to infinity? Let's do that calculation. So for the escape velocity, what we can say is the total energy is 1/2 m times the escape velocity squared minus the potential energy, which is g m over r. And we're going to take the total energy 0, which means this goes to 0, which means that for the escape velocity, as the object goes to infinity, right at infinity, it comes to rest. We could give it more energy and it could be moving at infinity, but that's more than it needs. This is the minimum amount of energy that it needs to get to infinity, is to get to infinity at rest, okay? Well, this immediately tells me that V escape is the square root of 2gm over big R. All right? Anyone notice anything interesting? What if R equals 2gm? What is the escape velocity?
The speed of light.
It's the speed of light, which is 1. Okay? Holy shit. In Newtonian gravity, we just predicted that if R is equal to 2gm, you have to be moving at the speed of light in order to escape. That's the escape, or this is the event horizon, and we know that if you're outside of the, holy shit, this is not general relativity, this just predicted a black hole. I like shit it did. This did not predict a black hole at all, period. Okay? First of all, if you are on the radius of this thing, and I thump you, you can go, even if R is bigger or R is less than 2gm, you can still move away. You might just come to rest and then come back. That is not the way a black hole behaves. A black hole behaves such that if you get to a value of radius less than 2gm, there is no movement outwards. The only movement you have is radial inward. This escape velocity, even if you don't achieve it, you can still move radially outwards. This is not an event horizon at all, period. An event horizon for a black hole is not something that once you go inside of it, you can mess around. Once you're inside of the event horizon, your only destination is the center, period. And we'll explore this next time, okay? But it's worse than that. This was you thumping it and giving it initial velocity. So say you thump it and you give it a slightly smaller velocity than the escape velocity. So it's going to travel out to here, it's going to come to rest, and then it's just going to turn its backpack thruster on and keep going. Why not? I mean, you can carry a little thruster and just keep going. You can have the biggest thruster in the world and aim it outwards, and you'll still go this way inside of a black hole. It doesn't matter how much thrust you can generate, period. Okay, that's it for today. Hopefully you're excited about next time. Next week will be a very interesting one for you, so be here if you can, all right? But I will send an email out tonight letting you know when I will hold office hours, because obviously many of you didn't hear, but I mistakenly logged into the wrong Zoom account last night and missed out on a couple of weeks. So I'll let you know when I'm having office hours and you can get help. And Madison will probably also hold our office hours again on Tuesday. Okay? Yeah.